What's up, team? This is Ro, your best friend at JMSB. So here I was asked a question for COMM 225, Production Operations Management. Let's have a look. A company builds custom equipment. It has landed a contract with a major customer. Relevant data are shown below. The complication is that the delivery has been promised in 32 weeks, and the company will have to pay a penalty of $375 for each week that the equipment is late. Lower down, we're offered a table with the various activities, the activities that they precede, their normal durations, and then their crash costs for the first week and for the second week. The question asks us to develop the minimum cost crashing schedule. So this is a very typical project acceleration or crashing question that I would expect to see on our midterms. Let's have a look together as to how we should approach this type of a problem. So whenever we're faced with a crashing question, the very first step is to draw out a project network diagram if one hasn't been offered to you, and to evaluate the current duration of the project. So in step 1, we're simply going to draw out a activity on node network diagram for our project, and we're going to evaluate the current duration of this project. In order to do that, we would be concerned with the activity column, the proceeds column, and the normal durations of each activity. Now in this step, we have to be careful. Sometimes we're offered a immediate predecessor column, in which case we have to draw the network diagram from the start node to the end node. Other times, like in the current case, we're offered a column that says proceeds, in which case we must draw our network diagram from the end node to the start node. So in this case, because it says proceeds, I'd recommend to begin by drawing out a node to represent the end of our project. Now starting from the bottom of our table, we're going to look at which activities precede the end node. And we can see that Z and Y precede end, and therefore in our network diagram, these two activities should be pointing towards the end ball. And now we're going to continue this logic. We can see that activity P precedes activity Z. So prior to activity Z, we're going to have activity P. Activity Q precedes P and Y, and so Q is going to come before P and Y. Activity J and M both precede Q, and so J and M are going to be pointing to Q. Activity N precedes J, and so N is going to come prior to J. Activity L precedes M, and so L is going to be pointing to the M ball. And then activity K precedes L and N, and so K should be pointing to L and N. Since activity K does not precede any other activity, we could argue that activity K is where the project sort of starts. So step 1 in tackling a crashing question is really to draw out a network diagram if one hasn't been offered to you already. Now once you've drawn out the activity on node diagram for this project, the next thing I'd recommend to do is to list every path that exists in your project and to evaluate the duration of each path. A path is simply a string of letters that is connected from the start node to the end node, and the duration of a path is simply the sum of the normal durations of the activities that make up the path. So lower down, what we could do is we could set up a little column for path along with duration. One example of a path is K, L, M, Q, Y. So a path is simply a string of letters that is connected from the start node to the end node. And how would you evaluate the duration of this path? Well, simply by adding up the normal durations of each of the activities that make up the path. So if I added up the durations of K, L, M, Q, and Y, I would figure out that the duration of this path is 32. So in the same way, what we want to do is we want to be looking at our network diagram, listing every single path that exists, along with the duration of these paths. So another path is KLM QPZ, and the duration of that path is 39. A third path is KNJ QY, and the duration of that path is 32. And the final path is KNJ QPZ, also with the duration of 39. So once you've identified each path that exists in your network and evaluated the durations of each of these paths, now you have the ability of determining which paths are the critical paths. I remind you that the critical paths or paths are simply the longest paths that exist in our network. And so in this example, the critical paths are paths KLM QPZ and KNJ QPZ. And that's simply because each of these paths have the longest duration, and their duration is 39 weeks. And so we can argue that the current duration of this project is 39 weeks. So in step one, this is precisely what I would do. I would first draw out a network diagram if one hasn't already been drawn for me, and then I would identify each of the paths that exist along with the durations of the path, and I would understand that the duration of the project is simply the duration of the critical path, which is the longest path that exists in the network. So the current duration of this project is 39 weeks. The next step to accelerate a project is simply to set up an iteration table and to go ahead and crash the project. An iteration table simply shows off the order in which activities are going to be accelerated in order to reduce the duration of the project. In our iteration table, we're going to have one row for activity crashed, a second row for the cost that is incurred, and then in the first two columns of our table, we're simply going to list the various paths that exist in our network along with their durations. So we've already identified the 4 different paths that exist in this project, we've calculated their durations, and so at this point I'm simply going to relist them in the first 2 columns of this table. And now that we have this table set up, I'm going to quickly remind you of the 3 rules to follow when you're crashing a project. The first rule is to always be crashing critical activities. The second rule is to remember to crash all critical paths simultaneously within each iteration. So whenever a project has more than one critical path that exists, at the end of each iteration, you really have to make sure you've shortened all of them. The third rule to remember is to understand that the choice of activities to crash is very closely related to their cost slopes. So the way you decide which activities you're going to be crashing is based on whichever activities are the cheapest. So this is going to be related to the cost slopes of the activities which are offered in our problem. So we were given each activity and what it costs to crash for the first week along with the second week. This table is going to be useful in deciding the cheapest way to accelerate the project. So now that we have this iteration table set up and we understand how the cost slopes work, the final thing I want to talk about before we tackle this problem is to know when it is that we're going to stop accelerating this particular project. In this example, we are told that the project has a deadline of 32 weeks and that the firm is faced with a penalty of $375 for every week that the project is delayed. Because of this penalty, it should be very obvious to you that you're going to keep accelerating the project as long as the cost incurred to shorten the project does not surpass $375 for that week. Simply because the minute that it does, it would be cheaper for the firm to pay the penalty. So now that we've understood these facts, let's go ahead and talk about our very first iteration and try to identify which activities we're going to be crashing. So in our first iteration, we're interested in shortening our 2 critical paths, path KLM QPZ and KNJ QPZ, in the cheapest way possible. So in order to identify the cheapest combination that is available to the firm, let's look at the cost slopes for the first week for each activity on the first critical path and begin by identifying the cheapest activity. So by comparing the costs of activity K, L, M, Q, P, and Z, we can see that activity Z is the cheapest on this first critical path. If we have a look at the second critical path between K, N, J, Q, P, and Z, once again activity Z happens to be the cheapest. So it should be pretty obvious to us that in the first iteration, we're going to be crashing activity Z, and that's simply because that's the cheapest way of reducing the duration of both the critical paths at the same time. So where it says activity crashed, we're simply going to say Z by 1 week. The cost that is incurred is a cost of 90, And because this cost that is being incurred is less than the penalty of $375, it would be worthwhile for the firm to perform this iteration. And now all that's going to happen is every single path that contains activity Z is going to be shortened by one time period. So if a path does not have Z, such as the first path, its duration is going to stay at 32. However, 39 is going to be reduced down to 38. The third path is going to remain at 32, and this path is also going to go down to 38. One tip that I could offer is that during the crashing process, the moment that a path is critical, it really has to remain critical throughout the process. So if these two paths are critical at the beginning, throughout the entire crashing process, they must remain critical. What should also be obvious to us is that at the end of the first iteration, because we've crashed activity Z, we can no longer crash this activity, and that's simply because it does not have a cost slope for the second week. So at the end of the first iteration, it is as though activity Z is no longer available for us to crash. So let's go on to the second iteration. In the second iteration, we're again looking at the cheapest way of reducing the duration of these two critical paths. I remind you that we're no longer able to crash activities P or Z. The next thing I would do is figure out the cheapest letter between K, L, M, and Q. So if we compare the costs of activities K, L, M, and Q, we can see that the cheapest activity is activity L. On the second critical path, we compare the costs of K, N, J, and Q, and between those activities, we can see that N happens to be the cheapest one at a cost of 45. And now what we want to ask ourselves is, would we rather crash activities L and N and spend a total of 125 plus 45, so a total of 170, or would you rather crash a common activity, such as K and spend 410, or Q and spend 200. Since the cost of the two cheapest letters together is cheaper than the cost of the common letter, which is 200, we're going to go with the two cheapest letters instead. And so in the second iteration, we're going to be crashing activities L and N by one time period. And the cost that's going to be incurred is simply going to be 125 plus 45, so 170. Because this cost of 170 is smaller than the penalty of 375, the firm would want to complete this iteration. At the end of this iteration, every path that contains activities L or N is going to be reduced by one time period. So the first path is going to go down to 31 since it has activity L. The second path would go down to 37. The third path down to 31 since it has activity N. And the final path would go down to 37 as well. Now once we've completed this iteration, it's important for us to sort of cross out the activities that we have crashed, so we can no longer crash activity L, and that's simply because it does not have a cost slope for the second week, and activity N has been crashed for the first week, but could still be crashed one more time at a cost of 45. So at the end of the second iteration, we can sort of cross out activity L. And so now that we've done that, let's have a look at the third iteration. Once again, we're interested in lowering the duration of the two critical paths in the cheapest way that is possible. On the first path, the cheapest letter that remains between K, M, and Q happens to be activity Q. On the second critical path, the cheapest letter is still N, but now it is cheaper for us to simply crash Q by 1 because this activity appears on both the paths. And so we're going to crash Q by 1. The cost of Q is 200, still less than the penalty of 375. And so the firm would want to complete this iteration, and every path contains Q, so the duration of each path is now going to be lowered by one time period. Once we've done this, we can sort of cross out the first week cost slope for Q, and that's because it's now been crashed by 1 week. If we want to crash this activity again, the cost would be 225. So this brings us to our fourth iteration. We're essentially just repeating this process. Once again, we're looking for the cheapest way of lowering the duration of both these two critical paths. And Again, it would be cheapest for us to crash simply activity Q, because Q is the cheapest one on the first critical path. It is also common to both critical paths. And so once again, we're going to say Q by 1. The cost is 225 this time, but it is still less than the penalty of 375, and so this iteration should be completed. Every path contains Q, and so the duration of every single path is now going to be lowered by 1 time period. At the end of this iteration, because we've crashed Q by 1 more week, we have now sort of exhausted by how much we can accelerate activity Q, and so Q would sort of be cancelled out as well. So let's have a look at the 5th iteration. This time around, we can't crash activities L, Q, P, or Z. So between K and M, the cheapest activity would be M with a cost of 300. On the second critical path, the cheapest activity is N with a cost of 45. And so since 300 plus 45 is still less than our penalty, we're now going to crash M and N by 1. So the total cost would be 345, and any path that has M or N on it is going to be lowered by 1 time period. At the end of this iteration, it's as though we have now max crashed N, since we've crashed it for the total of its 2 weeks, so we can no longer crash activity N, and we've also crashed M for 1 week, so this guy could be crashed for 1 more week. So let's now talk about the 6th iteration. If we were to continue this process, what would be the cost? The next time around, if we try to accelerate both these 2 paths, on the first path, we would be obligated to crash activity M, simply because it's the cheapest with a cost of 350. And on the second path, we'd want to crash activity J, simply because it is the cheapest with a cost of 50. But this time around, understand that the combined cost, 350 plus 50, 400, exceeds the penalty of 375. And so despite the fact that the firm is going to be 2 weeks late on its deadline, it's not worth it for the firm to further crash the project. They'd rather just pay the penalty, since it would cost them more to crash the project by another week than what the penalty is. So here we have it. I hope that this explanation helps you. I hope you guys keep practicing. And if these types of videos do help you, please make sure you spread that love by tagging your friends who are taking the class. In the meantime, I hope you guys study well, you keep well, row out.